Good day, everyone. We are Group GAB HAKDOG, and our topic is about horizontal circular curves. We will be discussing the definition, elements, and sample problem for simple, compound, reverse, and spiral curve. Compound and reverse curves are treated as a combination of two or more simple curves, whereas the spiral curve is based on a varying radius. I know a lot of you are familiar with this topic because we see it every day when we go out or travel. So, horizontal curves are circular curves or arcs used to change the direction or alignment of a road. Sharpness of the curve increases as the radius decrease, which make it risky and dangerous. Personally, sharp curves are dangerous because it is difficult to steer the wheel. In a car, you don't go directly from going straight to fully turning. Lastly, the design of the curve is dependent on the intended design speed for the roadway. Other factors include drainage and friction.
So hello everyone. Now we have the first type of horizontal curve, which is the simple curve. A simple arc provided in the road to impose a curve between the two straight lines. An arc of a circle. The radius of the circle determines the sharpness or flatness of the curve. The larger the radius, the flatter the curve. Now you can see the figure of a simple curve and its components or its elements. The point at which the alignment changes from straight to circular is known as the BC or the beginning of the curve. The beginning of the curve is located distance t or subtangent from the point of intersection, or which is the PI. The length of the circular curve is dependent on the central angle, and the value of radius are known as r. The point at which the alignment changes from the circular back to tangent is known as the end of the curve, or it could be EC. Since the curve is symmetrical about the PI, the EC is also located distance t from the PI. From the geometry, we recall that the radius of a circle is perpendicular to the tangent at the point of tangency. Therefore, the radius is perpendicular to the back tangent at the beginning of the curve, or BC, and to the forward tangent at the end of the curve, or EC. So here is the solution for the sample problem for simple curve. In the sample problem, the tangent and the length of the curve is already given, which is the tangent is 45.044 meters and the length of curve is 89.710 meters. If you want to know the formula for tangent, which is r tan deflection of angle over 2, while the length of the curve would be 2 pi r multiplied to deflection angle over 360 degrees. So to solve for the beginning of the curve, or the BC, we need the point of intersection, which is 0 plus 241.782. Then we need to deduct the tangent, which is 45.044. So if you deduct those two, the beginning of the curve would be 0 plus 196.738. Now since we have the beginning of the curve, which is 0 plus 196.738, to get the end of the curve, we only need to add the length of the curve, which is 89.7110. So BC plus L, or beginning of the curve, plus the length of the curve, which would outcome of end of the curve 0 plus 286.448.
Now, we have come to know that compound curves are mainly two or more curves between two main tangents joined. These are the elements of a compound curve, noting that it has the same as the simple curve, only adding another set of it, plus the point of compound curve. Let us now refer to the figure with the following given values. Angle delta is 11 degrees, 21 minutes, and 35 seconds, while the point of intersection, PI, is at 14 plus 87.33, and angle D being 6 degrees respectively. Now based on the problem, we have to calculate the station BC and EC. To start off, we need to determine the value of R, which would now be given at 954.93 feet, derived from 5792.58 divided by D, which is 6 degrees. We then identify the value of T with the formula R tangent delta over 2, having 954.93 tangent 5.679861 degrees, resulting in 94.98 degrees. We shall now seek the value for L, or length, of the curve, with the formula being 100 delta over D. Substitute, and we now have 100 times 11.359722 divided by 6, which now equals to 189.33 feet. Now, in getting the station BC and EC, we start at the given point of intersection PI at 14 plus 87.33, subtracted by the value we had for T, which is 94.98 feet, to solve for BC, giving us 13 plus 92.35. With this value, we shall add the length of the curve to it, which is 189.33, resulting in 15 plus 81.68. And this would be the simple explanation for the compound curve. Let us now proceed to the next reporter.
Now let's proceed to the reverse curve. So a reverse curve is a combination of two simple curves combined together to curve in the opposite direction. So it's basically just the combination of compound and simple, where simple is just only one curve and compound is a continuation of a simple curve. However, a reverse curve, it is a reversed form of the compound curve, if you know what I mean. So this is an illustration here from this slide. So it basically forms an opposite sided curve with two set of radiuses. Okay, so the elements of the reverse curve are the following. So the PC, which is the point of curvature, the PT, which is the point of tangency, the PRC, which is the point of reverse curvature, T1 is the length of tangent of the first curve, T2 is the length of the tangent of the second curve, V1 is the vertex of the first curve, V2 is the vertex of the second curve, I1 and I2 are essential angles for the first and second curves. So L1 is the length of the first curve, L2 is the length of the second curve, and we also have the length of the first chord and the second chord. And T1 plus T2 are the length of the common tangent measured from the vertex from the first curve to the second vertex, the second curve. So we'll discuss this furthermore. So in the illustration, so we have here the first tangent, which is located above here on the start of the point of curvature, and then we have the V1, which is the vertex of the first curve, because we are going to have a common tangent between the first and the second tangent here. There's a slant line in the middle, so that's a tangent. So, and it is still the same with the T2. So the T2 is always tangent to the radius too, and it's the same with the T1. So dapat tangent dyan sila, and dapat perpendicular sila to the radius, because it is the rule when dealing with curves or circles that the radius should be perpendicular to the tangent. Okay, so the PRC, which is the point of somehow an intersection between the common tangent and the curves. So these are called the point of reverse curvature, which means that it is an indicator that the curve should be in the reverse form. When we go to the second tangent line. Okay, and we have our I1, which is the central angle of the curve, which is, you know, an angle adjacent to the radiuses. And we have what we call the point of tangency, which is somehow the end of the tangent line, or an indicator to end tangent line. So it is also an indicator for the radiuses to put and how narrow or wider the curve is. So other variables like a chord is a segment between the PC and the PRC in terms of the curve 1 or tangent 1, and it is connected through the PRC, and the last segment should be at the point of tangency. So the chord is from PC going to the PRC just for the first curve, and from the PRC to PT for the second curve, and they are connected. So that's how very important, and is used to measure some variables. So we'll go to the example. In the sample problem number 5, so we have here a reverse curve problem. So a reverse curve with divergent tangent is to be designed to connect to 3 transverse lines for the proportion of the proposed highway. The lines AB is 185 meters, BC is 122.40 meters, and CD is 285 meters. The azimuth are due east 242 degrees and 302 degrees respectively. The following are the cost index and specification. So we have the type of pavement, which is item 311, a Portland cement concrete pavement. There are 2 lanes with the width of 3.5 meter per lane, with a thickness of pavement which is 280 millimeters, and the unit cost of 1,800 pesos per square meter. So it is necessary that the point of reverse curvature must be 1/4 to the distance BC from B. So the question is, find the radius of the first curve, then find the length of the road from A to D, so we use arc basis. In the last one, we find the cost of the concrete pavement from A to D. So before we answer, we have to discuss something that needs to be discussed. So in this slide, we have here 2 types of reverse curve, which is a parallel and non-parallel. So what is the difference between them? So as you can see in the figure for the parallel reverse, so the tangents between the curve 1 and curve 2 are parallel, which means they are not let's say they are the same in form, and they're not different in terms of it's just a form. So unlike to the non-parallel reverse curve, as you can see here, the tangent 1 has a horizontal line, whereas the tangent 2 has a slanting line, so they are not the same in form. So that's why we call that a non-parallel reverse curve. But nevertheless, the functions are always the same. So depending on the problem, we use different variables in order to get the necessary variables. So let's proceed to the problem. So we are here to the solution for reverse curve problem number 5. Okay, so we have here different formulas that are conditions that is stated a while ago. So first we have the first tangent, or T1. It is equal to 1/4 times BC. So as you can see here in the figure, we can substitute them, diba? So it's equivalent to 1/4 times 122.4 meters. So to equate that, we have an answer of 30.6 meters. Well, for the T2, we have subtracted 122.4 and 30.6. So why is that? Why we have to subtract 122.4 and 30.6? So in order to get T2, diba? So we have here line BC here to the first tangent. So we have here, as you can see in the blue line, we have T1, the segment T1 in the first radius. So it's measured as 30.6, diba? And T2 here from the yellow segment is unknown. So since we know the values of BC and D1, so we have to subtract them, and the answer is 91.8 meters here. Okay. So for the R1, diba, when we measure radius, we use a concept of trigonometry here, diba? So in R1, we divided T1 to tangent 14 degrees. Since 14 degrees is somehow like a half to the central angle, diba? So we have here 30.6, diba? 30.6 as T1, diba? Over tangent 14. Let's see, what's the value of tangent 14? So we have here tangent 14 is approximately 0.25. Okay, so when we divide them, we have an answer for 122.73 meters. So here in R1, which is in the blue segment here, labeled here, so the radius is 122.73 meters. And for the R2, we do the same. Okay, so we have tangent 2 over tangent 30, since 30 degrees is the central half the central angle here. From the yellow curve, diba? From T2, diba? That's the second curve, diba? So we have here 91.8 over tangent 30. Tangent 30 is 0.58. That's approximate value. So we have an answer of 159 meters. Okay, so we already solved this. So now we talk about the total length of road from A to D. Okay, this is an A to D. Diba? That's the start of the curve, like the point of curvature, and the D is, let's say, the end of curvature. Diba? So we have here the length is equal to 154.40 plus 2 pi. That's 2 pi times 122.73 times 28 degrees over 180. So technically, the formula is for this part is 2 pi times R1 times the degree of inclination of the curve inclination over 180, then plus pi times 159 times 60 degrees over 180 degrees. So what we're going to get here is I mean, like, it is in the second tangent, diba? So the third one is 193 plus 20, so it should be added also. So the length of total length of road from A to D is from the PC to the PT, diba? So the curve or the blue lines, that's what we are trying to measure for. Okay, so as you can see here that we already simplified the equation. So we have here L is equal to 154.40 degrees, plus 59.98 meters plus 166.50 meters plus 193.20. So the total length between A to D is 574.08 meters. Okay, in another figure, we have here like a complete detail with the road itself, with the width, the road width, the distance from the start of diba? From distance on the start of the curvature, like from point AB, that's 154.40. And we have here the radiuses, the radiuses, the central angles, diba? With the 193.20 and so on. Okay, now we are going to find the area of the road pavement, which is the formula of the 154.40, which is AB times 6.10. Because as you can see here, we can do this like murag. We are doing here a rectangle area from this part AB and the width. So plus pi times 119.68 plus 6.10, and that is the sum is squared, minus 119.68 squared times 28 degrees over 360 degrees. So then another one plus pi times 155.95 plus 6.10, and the sum is squared, minus 155.95 squared times 60 degrees over 360. So these two fraction equation is based on the different curves, diba? This is curve 1, the blue in segment, and the curve 2 is the yellow segment. So we add here by 193.20 that times 6.10 and 193.20 times 6.10. So it should be like 193.26 times 0. I mean like times 6.10, then the product is squared. Okay. So we have here the simplified form, which is 160.50 plus 365.86 plus 1015.68 plus 1178.52, and the answer is 2720.56 meters squared. So we are done getting the area, and lastly, the last question is to get the cost of concrete pavement. So we have here like a per square meter cost, which is 1,800 pesos, multiplied by the area, which is 2,720.56 meters squared, and we have the answer of 4,897,008 pesos. So I hope you understand, and if you have any question, just type it in our chat box.
The last horizontal curve we are about to talk today is the spiral curve. Spiral curve comprises a series of curves which have different radius. In case you are wondering if what is the difference between the compound and spiral curve curve are treated as a combination of two or more simple curves, whereas the spiral curve is based on a varying radius. This type of curve is used primarily to reduce skidding and steering difficulties by gradual transition between straight line and turning motion. Discussing on how to solve for the spiral curve will be kind of lengthy. To save time, here is a link and a QR code for sample problems and solution for spiral curve. Thank you for watching. I hope that this topic will help you in any way or in the future. When you're outside, you can now classify on your own on what type of horizontal, circular curve you see. Again, thanks for watching.